Hello, ladies and gentlemen. How are we doing today? It is Mr. Dorfler here with your daily dose of Dorfler. You might see me always trying to shift in my seat during these recordings. That's because how my desk is set up. Basically, my knees are always hitting the drawers on my desk. Everything has to be kind of set off to the side. I have to make sure this camera is easily accessible so I can use it to angle down to my little whiteboard here. So I feel like I'm always shifting because my chair's on rollers, and then every once in a while I'll move, and then my desk. I'm taking up too much of your time today because today I need you to get comfortable in your seat, on your couch, wherever you might be watching this video, because we're going to be covering a lot, and mainly because everything we talk about in this section, yes, it goes together really well. But also, if we try to split this section up into multiple videos, then you would most likely have to take the test on this during Christmas break. We don't want that. We want to make sure that we get completely done with this chapter before you take off for a couple of weeks. All right. So that leads us to this section. Okay. Section 4. Oxidation reduction reactions, otherwise known as redox reactions. Okay. Basically, what is occurring is we are really focusing on what is happening to individual substances, mostly like looking at how, like, ions, okay, when they are in a chemical reaction. We are really focusing in on what is happening to the electrons in a reaction, okay? And electrons are what make an ion or not an ion, okay? So let's talk about oxidation reduction. What do those mean? An oxidation, or when something is oxidized, it loses electrons, okay? Let's say that again. When something is oxidized, it loses electrons and therefore becomes more positive, if you will. When we have a substance or an object being reduced, or reduction occurs, okay, it's when we gain electrons. So something becomes more negative or less positive. Means the same thing, but also I wanted to say that to make a little more sense, okay? Now, in a redox reaction, you cannot have one without the other. If you have oxidation occurring, you must have reduction occurring. You got to have some place for that electron to go. And it's also vice versa. If you have reduction occurring, you have to have oxidation occurring too, because you had to have those electrons come from somewhere. All right. Now, I'm going to say something here. I'm going to try to use this example on the slide the best I can here. So we have calcium, solid calcium, that is reacting with gaseous oxygen, okay? And it's going to form calcium oxide. Now, if we were to look at these substances and try to break down or dissociate what we could into their ionic components, only the product could be dissociated. Now, that's not always going to be the case. You're going to have times where reactants can dissociate and so on and so forth. We'll see those here in a very short amount of time. But calcium is in its natural state, so it doesn't have a charge, okay? It's neutral. Oxygen is also in its natural state. It does not have a charge also. You might be asking yourself, what do you mean natural state charges? I'm going to get to that. Rules, okay? But when we get to calcium oxide, we dissociate that because it is an ionic component or compound, we see that we get calcium 2 plus and oxygen 2 minus, okay? Now, when we have redox reactions, we obviously see calcium went from a charge of 0. And when I say charge, I'm meaning charge loosely. We're going to supply what are called oxidation numbers here in just a few moments when we start talking about the rules. Okay. So calcium is going to go from an oxidation of 0 to an oxidation of +2. So it became more positive. Well, since it became more positive, that means that it had to lose electrons. Therefore, it was oxidized. And oxygen, starting off at 0, at the very end, now has an oxidation number of -2. Okay? So that means that it went from 0 to -2. So it became more negative. So that means it had to gain electrons. So it was reduced, okay? So calcium was oxidized because it lost electrons, because it went from a 0 to a 2 plus, and oxygen was reduced because it went from a 0 to a 2 minus. Now, I keep saying charges and oxidation numbers. For the most part, oxidation numbers are going to match fairly nicely with the ionic charges that we've seen in previous chapters. Not all the time, and there's a simple solution to figure out what that oxidation number will be. Okay, just hang tight. Now, got one other thing I want to get out of the way before we go any further. Okay, like I said, calcium was oxidized, oxygen was reduced. Here's where you need to kind of put in the back of your mind here. Since calcium was oxidized and oxygen was reduced, that means that oxygen was the oxidizing agent and calcium was the reducing agent. Stay with me? So calcium was oxidized. It makes calcium the reducing agent. It is reducing the other substances in the reaction. Oxygen was reduced. Therefore, it was the oxidizing agent. It was the one stripping away the electrons from the substance that was oxidized. Okay? You might need to replay that statement back a couple times. Put it down into a slower speed if you have to. Okay? Now, before we continue further, I want to show you a quick little mnemonic here, little saying. Okay? Can never get the coloring right on here. Okay. Okay, did it again. So, I want you to remember, and right off to the side of your notes, this little saying. Oil rig. Okay? I want you to write that down because there's another saying too called Leo the Lion Goes Grr. I don't like that one. Too much going on. I like oil rig. What this stands for is oxidation is loss of electrons. And I bet you can figure what this one is. Reduction is gain of electrons. So oil rig, oxidation is loss of electrons, reduction is gain of electrons. Okay? Jot that down. Pause the video, jot that down. Okay? Oil rig. All right. Back to me. I'm going to put the light back where it normally goes. Okay, back to me, back to notes. And we're going to continue on. If I can get my camera right there, we go. All right. So I mentioned oxidation numbers just not that long ago. To determine whether or not an oxidation reduction has occurred, we assign what are called oxidation numbers to each element in a neutral compound or charged entity ion. Okay? So here are the rules that you must obey. Ready? Elements in their elemental form have an oxidation number of 0. So like we saw in that example in the previous, or 2 slides ago with calcium and oxygen. Calcium and oxygen were in their elemental form. They were by themselves. They were in, calcium was a solid, oxygen was a gas. That is how you find them in nature. Okay? So they would have a an oxidation number of 0. That's why I kept saying calcium as a solid, in a reactant, was 0. So was oxygen as a gas. Okay? Continuing on with the rules. The oxidation number of a monoatomic ion is the same as its charge. So, like chloride. Chloride has a -1 ionic charge. Therefore, it'll have a -1 oxidation number. Let's look at oxygen. Okay? Oxygen, when it's an ion, has a 2- charge. Oxygen would therefore have a 2- oxidation number, but we're going to talk about oxygen here in just a moment, okay? Not always. Okay? Same thing goes for if we have metals, okay? If we have calcium, or we've already seen calcium. If we have potassium, okay? Potassium forms an ionic charge of +1. If it's an ionic If it's an ion in the problem, then it'll also have an oxidation number of +1. Okay? So nonmetals tend to have negative oxidation numbers, much like their ionic charges, although some are positive in certain compounds or ions. Now, yes, there are some points to where nonmetals may have a positive oxidation number. Again, these numbers are arbitrary, so don't panic. Okay. Oxygen, as I was just mentioning, typically has an oxidation number of -2, except when it's in a peroxide. We really haven't talked a whole lot about peroxides, and I tried to avoid peroxides when I can. If an oxygen is in a peroxide, then it'll have a -1. Hydrogen, moving on, is -1 when bonded to a metal. Okay, so if it's bonded to any of the 80% of the periodic table, which is metals. Okay, but if it's bonded with a nonmetal, then it'll have a +1. Okay, fluorine will always have an oxidation number of -1. The other halogens in group 7 will typically have an oxidation number of -1, except if they are in a situation to where they might be positive. This usually happens in oxyanions or polyatomic ions. Okay. The sum of the oxidation numbers in a neutral compound is 0. The sum of an oxidation number in a polyatomic ion is the charge on the ion. So raise your hand if you like algebra, simple algebra. Okay, raise your hands, raise your hands. I'm hoping that some of you actually did raise your hands at home, because that would be awesome. We are going to treat these oxidation questions just like algebra. Okay, let's look at these sample exercises here. Okay, let me get a little pointer out. So we have 1, 2, 3, 4, 5 sample questions that we are going to work at. And in all 5 of them, we need to determine the oxidation number of sulfur. Okay, only sulfur in these questions. So in the first one, H2S. Okay, so we're trying to figure out what S is. We were told in the rules about hydrogen and what oxidation number it will have if it's attached to a nonmetal. But as you also notice before we continue on, that H2S is a neutral compound. How do I know that? There's no plus or minus charge up on the upper right-hand corner. So if there's no charge there, that means it's neutral. So coming down here to the solve, follow my little mouse here. The subscripts, there we go, in these formulas are going to play a key role. Like we saw in the previous sections of this chapter, they're going to play a key role when you start breaking them down. Okay, so according to the rules, hydrogen has a +1 oxidation number when bonded to a nonmetal. But as you see here, there is a subscript of 2 on there. So I put 2 plus 1, I'm going to multiply those two, plus X. We provide X for the object that we are solving for, algebra. And we set it equal to 0 since, again, it is neutral. All their oxidation numbers have to add up, really, to 0. So I multiplied 2 times plus 1. Then I have plus X equals 0. I rearrange this to solve for X, and I find that X, or sulfur in this case, has an oxidation number of -2. And that's your answer. For B, we have S8. Okay, this is actually one of the most stable forms of sulfur. Okay, S8. So this is how it's typically found in nature. Since S8 is how we typically find it in nature, it means it's in its elemental form. Therefore, its oxidation number is 0. Next, we have SCl2. Okay, so again, we're going to make the S, we're going to give that an X in our problem. Cl2, excuse me, And we see that we have another neutral compound. So anyway, chlorine is going to have a -1 oxidation number, and there are 2 present. So setting this problem up here where my pointer is, we have X plus 2 times -1, again, this is for chlorine, is equal to 0. Solve for X, we find that this time sulfur is going to be a +2. Okay? So, again, in this situation, sulfur is going to be oxidized because it loses electrons. It went from essentially, it goes from a 0 to a +2. Next, we have Na2SO3. Okay, so this is one where we have a polyatomic ion. So, for D here, if you see sodium, it's an alkali metal, it's going to have an oxidation of +1 because it's in the alkali metal family and it typically has a +1 ionic charge. Oxygen typically has a -2 oxidation number. And so again, letting X equal sulfur, we have 2 times 1, again, coming up here to Na2, subscript of 2 times +1, plus X, plus 3 times -2. Again, that 3 came from the subscript of the O here. So you split apart your polyatomic ions into their individual components in order to solve for oxidation numbers. Excuse me. So when we do this, again, it's set it to 0. We solve for X. We find that sulfur in this case is a +4. So we've had all sorts of different oxidation numbers for sulfur here. And lastly, we have SO4 2-. Now we're getting into a situation to where we actually have a charge on this compound here, which is essentially a polyatomic ion. So again, we set it equal to X plus 4 times -2 is we set it equal to -2 because again, when we have a charge on the object or substance, we have to set it equal to that charge. And then we solve for X, we find that S has actually got a +6. So let's look at a couple of these here, okay? We got A, B, C, D, and E. Okay, so we are to determine the oxidation state or oxidation number of the bold-faced letter. So the first one is P2O5, where phosphorus is going to be there. Next we have NaH, where hydrogen is. In C we have Cr2O7 2-. We're looking at chromium. D is going to be SnBr4. Excuse me. And E is going to be a O2 with oxygen being there. And in D it's tin. Okay? So let's get into our setup here. Dim it down. Okay, so look at the first one. Okay, so again, we're solving for P. We know that P has a subscript of 2, so it comes out here, and we're going to put an X for P. We then look at oxygen. There are 5 oxygens. Each one we're going to put down for a -2 oxidation number, and we set it equal to 0. So here we get 2x minus 10 is equal to 0, and we just solve for x. So once we solve for x, we're going to get x is equal to +5. You must include the sign, whether it's negative or positive. You must include the sign. So +5 is your answer for A. Let's look at B. Sodium is going to be a +1. Hydrogen, we're solving for, it's going to give us an X, and it's neutral. So solving for X, you're going to get -1 for X. For C, again, setting up the same way. Chromium is our unknown. We have 2 chromiums, so 2X plus we've got 7 oxygens. Again, it's a 2-. But this time, it's set equal to -2 because of its charge there. So here we get 2x minus 14 equals negative 2. We get the x is equal to plus 6. All right, next we're going to SNBR4, where 10 is our unknown. So we give SN our x, plus we have 4 bromines, and so bromine is going to have a minus 1 oxidation number. It is neutral, and so when we solve for x, we get x is equal to plus 4. And lastly, BaO2, where O is what we're trying to find. It is a neutral compound. So Ba is going to be 2 plus 2x is equal to 0. Solving for x, we get, x is equal to minus 1. So since x, or oxygen, was a minus 1, we have a peroxide. Okay? But again, those are rare that we come into contact with those. So that's how you solve oxidation numbers. Again, it's just very simple and basic algebra. Okay, if you want to look those examples again, rewind the video. I'm going to continue on so we can get through all of these. Now, next, what we're going to talk about is we are going to look at something that we just did in previous section. Okay, we're going to be looking at displacement reactions, but also we're going to be utilizing ionic equations, okay, net ionic equations. So basically what we're going to be doing is we're going to be identifying substances that are being oxidized and substances that are going to be reduced based off of the net ionic equations and how the substances that are left appear in the beginning and at the end, okay? So in displacement reactions, ions oxidize an element. So if you look here, in this reaction, we have hydrochloric acid plus magnesium are going to react and form hydrogen gas and magnesium chloride. So when we have a displacement reaction, what's going to happen is when we dissociate the ionic substances or the electrolytes, one of the ions is going to oxidize this element. So in this case, magnesium. Okay. So this displacement reactions idea is also going to play into the last topic that we're going to talk about today. Okay. That's called the activity series, but we'll get to that in a little bit. So this example right here is exactly what we did in the last lab, where I put copper into a solution with an acid with silver nitrate, and we got this reaction. It's exactly what happened, okay? Where we can see silver forming here, copper ions go into the solution, and it turns blue. But anyway, in this reaction, it's already been broken down for us. It's already been turned into the net ionic equation. The silver ions oxidize the copper metal. So we see copper started off, okay, so it's in its natural form, it's in its solid form, okay? It is going to be oxidized by the silver. So silver nitrate, okay, was the solution, and now it's broken down into its ion. We see that copper was 0, silver was plus. After the reaction occurred, copper was 2 plus, and silver became a solid. Therefore, it's in its natural state, or its elemental form, and now it's a 0. So copper went from 0 to 2 plus, meaning it lost electrons. Silver went from plus to 0, meaning it became less positive. Therefore, it gained electrons, and that made it be reduced. So copper was oxidized, silver was reduced. So we're just looking at basically the oxidation values on these in a net ionic equation to help us determine who was oxidized, who was reduced. So if copper was oxidized, that makes copper the reducing agent. And if silver was reduced, that makes silver the oxidizing agent. I'm going to keep saying that over and over again. However, if we try to take this reaction here and go backwards, it doesn't happen. Okay, it's a one-way street for this particular reaction. So let's look at this example here. We are to write the balanced molecular and net ionic equations for the reaction of aluminum with hydrobromic acid. So here we are, right here. Okay, follow along with my pointer, folks. Here is the balanced equation with aluminum and hydrobromic acid. Again, this follows kind of like that do-si-do mentality that we just saw in the last section, okay? Switching partners. Aluminum and hydrobromic acid. Aluminum is going to switch partners with bromine, and hydrogen is going to be all by its lonesome, okay? So then, once we do the balanced chemical equation or molecular equation, we then have to do the ionic equation. We have to identify who can be dissociated. Well, hydrobromic acid is a strong acid, as we saw on the list, and so it can completely dissociate. Aluminum bromide is an ionic substance, and it's aqueous, so it can dissociate as well. So once we've got our ionic equation, we then go and find our spectator ions, which in this case is going to be bromine, because bromine is identical both on the left and right-hand side. Aluminum does not have a charge on the left-hand side. It has a charge on the right-hand side. Hydrogen has a charge on the left-hand side and does not have a charge on the right-hand side. So those have changed, okay? So bromine was our spectator ion. And so it gets removed, and we write the net ionic equation as we see here on the very bottom. Sorry, I got something in my eye. We have 2Al solid plus 6H plus aqueous yields 2Al3 plus aqueous plus 3H2 gas, okay? So if we look at what's left in our ionic, sorry, I got something really bothering my eye. We see that aluminum is in its elemental state. It's a solid, and therefore it would have an oxidation number of 0. Over on the right-hand side, after the reaction has taken place, aluminum has an oxidation number of 3 plus. So it went from 0 to 3 plus. It became more positive. So it had to lose electrons. That means that aluminum was oxidized. Again, oil rig. And since oxidation and reduction always occur together, that means the other remaining substance, hydrogen in this case, went from a +1 charge to its elemental form of 0. So it went from +1 to 0, meaning it became less positive. Therefore, it gained electrons, and therefore hydrogen was reduced. So aluminum was oxidized, making aluminum the reducing agent. Hydrogen was reduced, making it the oxidizing agent. I told you I'm going to be saying that every time. Okay. Next, let's look at the practice exercise. Okay. We're going to do the same thing what we just did in the sample. Okay. We are to write a balanced molecular and net ionic equations for the reaction between magnesium and cobalt 2 sulfate. And then we are going to determine what is oxidized and what is reduced in the action. Gotta have some chapstick. Can never leave home without it. Okay, so going to my camera here. I'm going to dim it. Maybe dim. Okay, did not do anything. Okay, so again, we are having the reaction of magnesium and cobalt 2 sulfate. So let's get a little higher vantage point here. So we have magnesium in its solid natural state plus cobalt 2 sulfate. It's going to be an aqueous. It's going to yield, again, we're going to do-si-do. Cobalt and magnesium are going to switch places. Okay, we're going to have magnesium sulfate and cobalt, which is a metal. It's going to be solid. Okay. We're going to check to see if this was balanced. Yes, it's balanced. You can check it if you want to, but it's balanced. So This is the molecular. We're then going to do our ionic before we get to our net ionic. Okay, so magnesium plus cobalt 2 sulfate is an ionic substance, therefore a strong electrolyte. So we're going to have cobalt 2 plus because we're going to put its oxidation, or in parentheses ionic charges here. Okay, and it's aqueous plus SO4 2 minus aqueous will yield Mg2 plus, because based off of how we formed this this product here, we had we're gonna have a 2 plus because of the ionic charges, plus SO4 2 minus, okay, plus CO, it's C little o, solid. Okay, so that's our ionic equation. Now we have to identify who is the spectator ions. Well, magnesium went from a 0 to a 2 plus, so that changed, and it also went from solid to aqueous. Cobalt went from a 2 plus aqueous to a elemental form solid. And sulfate, well, it didn't change at all. It is the same on both sides. So that is our spectator ion. So our net ionic, our Ni equation, is going to be Mg solid plus CO2 plus aqueous yields Mg2 plus aqueous plus CO solid. Okay, so we checked off the balanced molecular equation. We've checked off the net ionic equation. So that's part A. Next, we need to figure out who was oxidized, who was reduced. Well, magnesium started off in its elemental form, and so therefore it has a 0 there. It ended up with a oxidation number of 2 plus. So it went from 0 to 2 plus, meaning it became more positive. So therefore it had to lose electrons. So magnesium was oxidized. It's also the reducing agent. Okay? So that means that cobalt it's the remaining substance here in our net ionic equation. It means cobalt went from a 2 plus aqueous to its natural solid state, therefore 0. So 2 plus to 0, it became less positive. Therefore, it was reduced. It had to gain electrons to become less positive. Therefore, it's the oxidizing agent. And so that's how we use net ionic equations to help us determine who is oxidized and who is reduced in a reaction. Now, staying with this concept of oxidation, reduction, and net ionic equations, we're going to use the last bit of our notes here. I don't know why it didn't go back to normal, but oh well. And we're going to talk about the activity series, okay? We use an activity series to help us determine whether or not certain metals are going to be oxidized before a reaction ever takes place. Different metals are going to vary in the ease with which they are going to be oxidized. So some metals don't like to have their electrons stripped away from them. So basically, they said they don't like to react. Activity series is going to arrange those metals in order of decreasing ease of oxidation. So the higher up a metal is on this series that we're going to see, the easier it is to strip away electrons. The easier it is, therefore, to be oxidized. The alkali and alkaline earth metals are the most easily oxidized because think about this. They have those electrons that are in their outermost shell that are just like 1 and 2, and they're making them not real 100% stable. So they're like, yes, get rid of my electrons, please. I don't want them. Take them away. So that's why the alkali and alkaline earth metals, again, going back to like chapter 2 right now, are easily oxidized. They're easily having their electrons stripped away. Metals towards the bottom that we're going to see real quick usually make up coins and jewelry because they don't like to be oxidized or are less easily oxidized and therefore don't necessarily always react. So that's why, gold and silver and copper and everything, they tend to be used fairly often in those instances because they don't like to oxidize, therefore they don't like to react, and so you'll pretty much always have the same jewelry after a long time. I'm going to get back to those are the questions that we do in the practice, okay? So here's the activity series, okay? What we need to do when we are looking at the activity series and trying to figure out if a reaction will occur, what we do, and I'm going to go back to, let's go back to this equation, all the way back to your displacement reaction, okay? Here we have a strong acid reacting with a metal by itself, okay? Stay with me here. If we have a situation to where, I lost it. If we have a situation like this, okay, where this was silver nitrate, as we see here, okay, reacting with copper metal, okay? If one of these is, if this metal right here, if this standalone metal, okay, standalone metal, the metal that's by itself on the reactant side, is above the metal ion in the substance it's reacting with, then you will have a reaction. If this metal, the standalone metal, is below this metal ion in the activity series table, there will be no reaction, okay? So let's take a look at this. Excuse me. Will an aqueous solution of iron 2 chloride oxidize magnesium metal? If so, write the balanced molecular and net ionic equations for the reaction. Okay, so we have to look at the activity series to help us determine whether or not we have a reaction that's going to take place. So we're given FeCl2. This should actually, it's iron 2 chloride, and the metal Mg. So if the reaction occurs, we're going to see that magnesium should be located above the iron ion. Say that 3 times fast, okay? So magnesium is right here. Iron is right here. So magnesium is above iron in the activity series. Therefore, a reaction will occur. So then we go into the second part where we do our balanced chemical equation. We do-si-do the metals. So magnesium solid plus iron 2 chloride yields magnesium chloride and iron. And so then we do their ionic equation and then do our net ionic equation after we've determined who our spectator ion is, and we get this as our final answer, okay? This shows that magnesium went from a solid, therefore a 0 oxidation number to a 2+, so it was oxidized. And iron was reduced. It went from a 2+ to a 0. So now what we need to do is, we're not going to have to do the balanced chemical equations on here. We simply have to determine whether or not a reaction will take place. So which of the following metals will be oxidized by lead to nitrate? So we're going to be looking at where lead is located on the periodic table in relation to these 3 substances. So let's look at zinc first, okay? Zinc is right here. Lead is right here. So zinc is the standalone metal and is above lead in the activity series. Therefore, zinc will be oxidized by lead to nitrate. But yes, we will have a reaction here. Okay? We will have a reaction here. Yes. Why? I don't understand where that became larger than it used to be. Okay? If someone knows, please let me know. So zinc should be circled. Yes, zinc will be oxidized. Copper. Okay, got to find copper. Copper is right here where my arrow is. Lead is here. So copper is actually below lead. Since copper, the standalone metal, is below lead ion, there will be no reaction. So copper will not be oxidized by lead to nitrate. And lastly, iron. Okay, iron, we got to find iron, which is right here. Lead is right here. So the standalone metal of iron is above lead. Therefore, iron will be oxidized by lead 2 nitrate. So zinc and iron will be oxidized by lead 2 nitrate. Copper will not. That's all based off of their standalone metals location in conjunction with lead's location on the periodic table. Okay. Oh, that gets us to the very end of section 4. When we get to the next section, we're going into a little bit of math here, but nicely enough, it's going to be all formula based. So we're going to be talking about what molarity is. Anyway, I'm going to stop this video. I apologize for being extended, but again, they are all tied together, and we just had to get this done in one day. So have a good day. I'll see everybody later. Bye-bye.